In this video, we will learn about confirmatory factor analysis. So we'll start with an overview of what confirmatory factor analysis, or CFA, is. We'll talk about what path diagrams are, what model identification is in this context, what model fit indices are, as well as their cutoffs, and we'll also discuss how we interpret parameter estimates for confirmatory factor analysis models, as well as how we do model comparisons. So let's start with an overview of confirmatory factor analysis. So confirmatory factor analysis is a latent variable modeling approach used for evaluating measurement structure or measurement models. It is part of the structural equation modeling family of analyses. CFA, or confirmatory factor analysis, is used to evaluate the internal structure of a measure designed to measure a theoretical construct. Now, CFA is also a useful tool for evaluating construct validity. So in CFA models, theoretical constructs are represented as latent factors, which are also referred to as latent variables. And so here you can see a latent construct represented here conventionally by an oval or a circle shape. Now, in reflective measurement models, which is what we're going to be focusing here today in this video, the latent factor is specified as the direct cause of observed variables. Thus, the observed variables are considered indicators of the latent factor, like this. So here you can see this latent construct or latent factor here has 4 different indicator variables here. And these are observed variables, meaning these are things that we actually directly measure. So this is what our data set contains, our measurements or scores on these 4 indicators here. And we would say that these are reflective, hence reflective measurement models of this latent factor or construct here. Now, CFA, or confirmatory factor analysis, is very useful for what we call multi-item measures, meaning measures that have multiple indicators or multiple variables or items. So when working with people data, we often attempt to measure a relevant psychological construct or theoretical construct, which is often multifaceted in nature. And sometimes we refer to constructs as concepts. So over here you can see a circle. This could also be ellipsed or oval shape, because again, circles or ovals represent constructs or theoretical constructs. Now, a construct, as I noted, tends to be multifaceted when it's psychological in nature, meaning that there's multiple subfacets that help us explain what we would call the construct space. So let's look at an example here with a multi-item extroversion measure, where extroversion is one of the big 5 personality dimensions. So like many constructs, extroversion is multifaceted, which means that extroversion is made up of subtraits or subfacets that are all important interrelated elements of the extroversion construct space. So here's an example with extroversion here. Again, the dark blue circle, this is the construct or construct space for extroversion. And here we have in the light blue circles, talkative, sociable, outgoing, and enjoys socializing. These are the subtraits or subfacets or just facets of extroversion. So collectively, the facets of a construct help us define the construct space, which allows us to create an appropriate conceptual definition, where the conceptual definition or operational definition is used to define that construct or construct space. So for example, let's take this direct quote conceptual definition from Bauer and Erdewin's textbook from 2021 for extroversion, where they define extroversion as being outgoing, talkative, sociable, and enjoys socializing. And so you can see very clearly in this conceptual definition how there are specific facets or subtraits that are referenced here and then included here as facets within the construct space. Now, a multi-item measure is typically used to best capture the full space of a construct like extroversion because it does have multiple facets or subtraits associated with it. So over here you can see our construct and construct space as well as the conceptual or operational definition for extroversion that we saw previously. And then over here to the right in a square or a rectangle here, we see our extroversion items or questions listed here. Here we have 4 different items, And then we would expect that these items would map onto that conceptual definition here to try to tap into those various facets and subtraits associated with extroversion as we're defining it here. And you can see here, this is actual items drawn from Goldberg et al. From the IPIP Personality Inventory Project. And we see that here are the 4 items, such as I make friends easily, I am skilled in handling social situations, I'm the life of the party, and I feel comfortable around people. And let's imagine we're having people respond or rate themselves along these 4 items here using this strongly disagree to strongly agree 7-point response scale or response format. So when we put it all together and we actually want to estimate and evaluate the measurement structure and measurement model for a construct like extroversion, we can specify a single or one-factor CFA model like you see here, where again, the latent factor, the construct, is represented by this oval or circle here, this dark blue oval or circle that says extroversion. And then down below it, we see each one of the indicators, or items in this case, that are reflective of this construct of extroversion. So what we're seeing here is called a path diagram, and we're going to unpack that more in just a moment. So again, this is an example of a confirmatory factor analysis model path diagram. So let's talk about path diagrams and what they are and why they're useful. So commonly, we visualize our confirmatory factor analysis model as a path diagram, as this can help us understand and see what it is, in fact, that we're estimating and how we've actually specified our model. So let's first learn what the path diagram symbols are. So the conventional path diagram symbols are as follows. When you see that oval or circle, that represents a latent factor, which again is sometimes referred to as a latent variable. In this case, in this context, if we're trying to measure a psychological construct, that psychological construct is going to be represented as the latent factor or latent variable. If you see a square or rectangle, this is conventionally going to represent any variable that we've actually observed or directly measured. And in the context of confirmatory factor analysis specifically, sometimes we refer to these as observed indicators or just indicators. Anytime you see a single directional arrow where there's just a single direction or point to it, we call this a directional relation or a path, or in the context of confirmatory factor analysis, a factor loading. Anytime you see a double-headed, smaller line or path, something like this, where you see that there are 2 points to it, and it's smaller in nature, and this would be attached, for example, to a latent factor, visually speaking, this is going to represent commonly a variance component or a variance term. Now, if you see a larger or a longer double-headed arrow here with 2 different points, again, but it's going to be longer as it's going to be connecting either multiple latent factors or latent factors with observed variables or any combination of those, this is going to represent a covariance or a correlation if it's standardized. We also have what are referred to as residual error variance terms or uniquenesses, or sometimes just called disturbance terms. And these are going to be represented here by these little circles with a little e in them to represent error, and then you also see that variance component here. You see that variance symbol with the double-sided arrow here that is curving along and touching either 2 different points on this circle here. Lastly, and we're not actually going to focus on this in the remainder of this video today, there is also another symbol I want to bring to your attention. Anytime you see a triangle, it often indicates that there's a constant or a mean that's being estimated as a parameter in the model. So again, here are all the conventional path diagram symbols. You'll see some variations on these depending on whose work you're looking at, but generally it looks something like this. So let's apply the path diagram symbols to visualize the following path diagram examples that are specific to confirmatory factor analysis. So we'll start with a one-factor CFA path diagram, and then we'll look at a multi-factor CFA path diagram. So starting with that one-factor CFA path diagram, Here's a simple version where let's imagine that the construct that we're trying to assess with a multi-item measure is role clarity. So in other words, how well someone understands their job and their responsibilities at work. You can see that there are 4 different items here. So you can imagine there was a measure administered as part of a survey to employees where there's 4 different unique items that people were responding to and rating themselves on. So we have item 1, 2, 3, and 4, and these are represented again with the rectangles here, whereas the latent factor is represented with that oval. So when we talk about a multi-factor CFA path diagram, it's going to look something like this, and we'll actually break this one down and all of the different symbols associated with it. So here is a multi-factor, and more specifically a 2-factor CFA path diagram, where we have 2 latent factors here. One for role clarity, which is the construct of interest over here, and the other for task mastery, which is really about someone's self-efficacy or how confident they are and their ability to do their task at work. Okay? And so here each one of them has its own respective set of indicators, okay? Where in this context, the indicators are observed items or measures of items that we've given to respondents or employees as part of, let's imagine, a survey. So you'll see for role clarity, there are 4 different items that are loading onto this factor or that are reflective of that factor. That's item 1, 2, 3, and 4. And then for task mastery, there's 4 separate items, which are item 5, 6, 7, and 8. So let's unpack the different symbols here in this path diagram. So again, starting here, you'll see that the latent factors for role clarity and task mastery are represented visually with an oval shape here. Now we see the variances of those latent factors are represented with that little double-sided arrow here with the 2 points. And we see that that's just perched on top of each one of these ovals representing the latent factors. We see the covariance represented by that longer double-sided arrow here, and if we were to standardize that, that would become a correlation between the 2 latent factors. Now, these directional arrows here that are pointing from each of the latent factors to their respective indicators, these are our factor loadings here. You can see these represented in blue here. So you can see that what we're talking about here conceptually is that the latent factor is a direct cause, so to speak, of each one of these indicators, which again, the indicators here are survey items or measure items. Now, the items themselves are going to be represented in those boxes or those rectangles here because they are observed variables or indicators. And then we have our residual error variance terms, which again are sometimes referred to as uniquenesses or disturbance terms here. And those are going to be represented down here in blue with the circle and the arrows pointing to each one of the items. So this is any of the leftover error variance that's not explained by the latent factor in terms of each one of these indicators, or more specifically, items here. So now let's shift gears and talk about model identification now that we have path diagrams squared away, and hopefully we feel more comfortable unpacking and diagnosing what a path diagram is demonstrating to us or showing. So when we talk about model identification, let's start with what is referred to as a just identified model. And this is going to be a model with 0 degrees of freedom, which conventionally we abbreviate as DF, which you can see here. And what does that mean? Well, it means that the number of parameters, for example, paths or directional paths, factor loadings, variances, covariances, etc., that the number of parameters specified in a model is going to be equal to the number of unique or non-redundant sources of information. And we'll explain more what that means in just a moment. Now, with an over-identified model, our degrees of freedom for the model is going to be greater than 0. And so what this means more specifically is that the number of parameters that we've specified in the model is less than the number of unique or non-redundant sources of information that we have access to in estimating the model. Now, lastly, we have a model type that's called under-identified, and this is when our degrees of freedom are less than 0, meaning that they're going to be negative. So this occurs when the number of parameters that are specified in the model is actually greater than the number of unique or non-redundant sources of information, which is not a good thing for model estimation purposes. So when we have a just identified model where the degrees of freedom is equal to 0, the model can be estimated, but model fit cannot be assessed using the traditional types of model fit indices that we're going to cover later on today. When we have a model that's over-identified, where again the degrees of freedom are greater than 0, the model can be estimated and the model fit can also be assessed. And then lastly, with the under-identified model where the degrees of freedom are less than 0 or negative, the model fit indices and the parameter standard errors cannot be estimated. So let's talk about model identification now. So when we're talking about model identification, we're really referring to what are those sources of unique information or non-redundant information that we have access to in our data, and specifically the variables that are observed that we are specifying within our confirmatory factors analysis model. So the formula for computing or calculating what are the number of our non-unique or our unique or non-redundant source of information is very simple, okay? Where P in this formula is going to represent the number of observed or manifest variables in the model. Okay, so these are the variables, again, that appear in those rectangles. These are things that we've actually measured. So it's just P plus 1 times P, and all of that divided by 2. So let's work through an example here. So here's that same path diagram that we saw for role clarity earlier here, where again we have those 4 items. So for this one-factor CFA model, which consists of these 4 observed variables, which again in this case are 4 items from a measure that's part of a survey, the number of unique non-redundant sources of information is going to be equal to 4 plus 1 times 4, which is going to be 20, divided by 2, which gives us 10. So we have 10 unique or non-redundant sources of information. Now, you might be wondering over here, what is this little 1.0 that I placed here on the first factor loading that goes from role clarity to item 1? Well, typically the first factor loading is going to be one that is automatically specified by whatever kind of modeling software that we're using. We can also override that and specify another item to have this factor loading of 1, but the reason that we constrain one of the factor loadings to 1 is that it helps us scale the latent factor, which is referred to as scaling, and it can also help with model identification as it frees up a degree of freedom there for us. So how do we determine the number of free parameters then? Well, that constrained factor loading of 1.0, that's a constraint, so that's not going to be freely estimated. But what we can do is count up everything else that's going to be freely estimated, and these are referred to as the free parameters in our model. So first is going to be that variance of our latent factor, which I've labeled 1. And then we have the factor loading for item 2, item 3, and item 4 here. And then we have the 4 different disturbance terms, which again are referred to uniquenesses or residual error variance terms here represented. So we have 8 free parameters that we're estimating in our model. So if we take the number of unique sources of information, which is 10, which we calculated just a moment ago with that formula, and we subtract from it are the number of freely estimated parameters in our model, that gives us 10 minus 8, which is going to be equal to 2. So because the degrees of freedom is greater than 0, we would say that our model is over-identified, which is a good thing. This means that we can get, when we estimate the model, those conventional indicators or indexes of model fit and evaluate those. And we also will get our parameter estimates and their associated standard errors. So let's now shift gears and talk about those model fit indices that I've alluded to previously. So when a model is over-identified, where again the degrees of freedom for the model are greater than 0, the fit of the model to the data can be assessed using various fit indices, which we're going to go over. So the 5 that we're going to focus on are the chi-square test, the comparative fit index, which is CFI, the Tucker-Lewis index, which is TLI, the root mean square error of approximation, which RMSEA, and finally the standardized root mean square residual, or SRMR. Now, Hugh and Bentler's 1999 simulation study is one of the most widely cited sources when it comes to recommended cutoffs for model fit indices. And more recently, NIE in 2023 provided a concise summary of those recommended cutoffs. So that's where I'm going to be drawing in the subsequent slides here. I'm going to be drawing from those two sources in terms of suggesting different cutoffs that are pretty conventional, at least in the psychological management and more specifically industrial and organizational psychology literatures when it comes to model fit in structural equation modeling in general, as well as more specifically in the context of confirmatory factor analysis. So let's start with that chi-square test. So the chi-square test can be used to assess whether the model fits the data, where a statistically significant chi-square value, such as one where p is less than 0.05, indicates that the model does not fit the data well, whereas a non-significant chi-square value, one where p is greater than or equal to 0.05, indicates that the model fits the data reasonably well. So the null hypothesis that we're trying to determine whether we should reject or fail to reject that null hypothesis is that the test is that the model fits the data perfectly. Okay? So if we fail to reject that because our p-value is greater than or equal to 0.05, we're essentially saying that our model fits no worse than a perfectly fitting model, which is a good thing. Now, I should note that the chi-square test is sensitive to sample size as well as non-normality in the variables that we're modeling. So now let's shift gears and talk about the comparative fit index, or CFI. As the name implies, the CFI is a type of comparative or incremental fit index. And this means that the CFI compares the focal model to a baseline model, which sometimes is referred to as our null model or our independence model. Now, CFI is generally less sensitive to sample size than the chi-square test, which is good. And a CFI value greater than or equal to 0.95 generally indicates good fit or acceptable fit to the data. However, sometimes we'll relax this to 0.9, meaning that if the CFI value is greater than or equal to 0.9, we will consider that fit as being adequate or acceptable. Next, let's talk about the Tucker-Lewis index, or the TLI. So the TLI is a type of comparative or incremental fit index, just like the CFI. So this means, again, that the TLI, like the CFI, compares the focal model to a baseline model, which you could refer to as the null or the independence model. Now, TLI is generally less sensitive to sample size than the chi-square test as well. And a TLI value greater than or equal to 0.95 indicates good fit to the data. However, sometimes this is going to be relaxed, just like with the CFI, to 0.9. Now let's move on to the root mean square of approximation, or the RMSEA model fit index. So the root mean square error of approximation, or RMSEA, is an absolute fit index, okay? So not a relative fit index. And that means that it penalizes for model complexity, meaning that the larger the number of parameters that we're trying to estimate, the more that the RMSEA is going to be penalized. And so thus this ends up effectively rewarding simpler or more parsimonious models. Now, RMSEA values tend to be upwardly biased when the model degrees of freedom are fewer, meaning we have fewer degrees of freedom in our model. Now, an RMSEA value that is less than or equal to 0.06 generally indicates good or acceptable fit to the data, although sometimes we might relax that to 0.08 or even to 0.10. So lastly, let's talk about the model fit index that's called standardized root mean square residual, or SRMR. So this is another example of an absolute fit index, just like the RMSEA we just looked at. Now, an SRMR value that is less than or equal to 0.06 indicates good fit to the data, although some might relax that to 0.08. So here's a summary of those model fit index cutoffs that I've mentioned, and you might find this to be a helpful reference here. So you can see all of them listed here, and I have both the stringent cutoffs as well as the more relaxed cutoffs listed here as well. So a couple other things that I want to mention when it comes to model fit index cutoffs is that the conventional cutoffs for model fit indices, like any rule of thumb, should be used with caution and with good judgment. And these indices don't always agree with one another. And so there's somewhat more of an art compared as opposed to a science when we're evaluating models with these model fit index cutoffs. Now, generally, it is not advisable to interpret model parameter estimates unless the model fits the data reasonably well. Although we should also avoid, quote unquote, tossing out a model entirely if it shows marginal fit, or if maybe a few of the model fit index meet the cutoff and a few of them don't. We should look to see if there's any way that we can tweak the model, respecify the model in some way, and perhaps look to theory and other empirical evidence as well to see if there's ways that we can improve model fit. Now, I do want to note a recent advance, and this is called a dynamic fit index cutoff. And so dynamic fit index cutoffs represent a more recent advance in evaluating model fit, and they recognize some of the limitations of earlier work that suggested those widely used cutoffs that I've been referencing so far. And this work is really spearheaded by McNeish and Wolf, and I'm especially referencing their 2023 paper here. And so essentially what they have come up with is Monte Carlo simulation-based approach for estimating what these cutoffs should be for your specific model with your specific data. So now let's talk about parameter estimates. So let's assume that those model fit indices indicated that our model fits the data reasonably well. Well, in that case, we should feel relatively confident going forward and interpreting the parameter estimates in the model. So in CFA models, there are various types of parameter estimates, which correspond to the path diagram symbols covered earlier. So again, those parameter estimate types include covariances, variances, factor loadings, as well as residual error term variances and things like that. Now, when a model is just identified or over-identified, we can estimate the standard errors for freely estimated parameters, which allows us to evaluate statistical significance as well for those parameters. Now, with most software applications, we can request standardized factor loadings, which can help facilitate interpretation of these parameter estimates. And so we'll work through the major types of parameter estimates that you're going to encounter with the confirmatory factor analysis model. So let's start with factor loadings. So here's our old friend here, the role clarity one-factor CFA model that we've been working with here. And you can see here with the blue directional arrows there, unidirectional arrows, I should say, we have standardized factor loadings here, 0.78, 0.83, 0.81, 0.90. So how do you interpret those and what do they mean? So when we use standardized factor loadings, we obtained estimates for each directional relation between the latent factor and an indicator, including the factor loading we likely constrained to 1.0 or just 1 for scaling and model identification purposes. Now, when standardized factor loadings can be interpreted, when standardized, the factor loadings can be interpreted like correlations, okay? So that the upper limit should approach 1, the lower limit 0. Now, when evaluating factor loadings, we generally want to see standardized estimate values somewhere between 0.50 and 0.95. When a standardized factor loading falls outside of that range, we typically investigate whether there is a theoretical or empirical reason for the estimate and why it's out of bounds there. And we may consider removing the associated indicator in this specific context, that measure item, if it seems warranted on a theoretical basis, for example, or if there's a strong empirical rationale for doing so. So here you can see all of our factor loadings here are within that good range of 0.50 to 0.95. So we'd be pretty happy with this. Now let's talk about residual error variance terms and how we interpret those. So again, same model here, but now we're going to focus on the residual error variance terms, which are specifically down here, and they are standardized as I've noted down here. So we have 0.11, 0.39, 0.48, and 0.26 for items 1, 2, 3, 4, respectively. So the residual error variance terms, which are also known as disturbance terms or uniquenesses, these are going to indicate how much variance is left unexplained by the latent factor in relation to the indicators. So you can see here, again, we have these directional arrows for role clarity. When role clarity is predicting or causing, conceptually speaking, item 1, for example, this residual error variance term here represents the leftover variance that's not explained by the latent factor in our item, okay? Or more broadly, we would say this is the indicator. So when standardized, the error variance terms, and these are standardized to remind you, when standardized, these error variance terms represent the proportion of variance not explained by the latent factor. Okay, so, and if we multiply a proportion by 100, we get a percentage. Okay, so let's practice interpreting one of these. So let's look at that standardized residual error variance term of 0.11 that's associated with item or indicator 1 here. Now, again, it's 0.11, and so this actually indicates that the raw clarity latent factor explains 89% of the variance in the item 1 indicator. And so how did I calculate that? Well, I took 1 minus 0.11, or in other words, 100% minus 11%, and that gives me 89%. So ideally, we want to see standardized error variance terms that are less than or equal to 0.50, meaning we don't want too much leftover variance unexplained after we account for the effect of our latent factor on that particular indicator. So now let's talk about variances in the context of a CFA model. So here you can see the variance term represented here by this smaller curved double-sided arrow here, and we can see that this is an unstandardized estimate, which I've indicated down here, and it's 0.60. Well, the variance estimate of the latent factor is generally not going to be a focus when we're evaluating parameter estimates in a CFA model. So the variance of a latent factor is going to depend on the factor loadings and the scaling, so it's not usually of substantive interest. But what is of substantive interest is when they are around our covariances or correlations as parameter estimates in our model. So here's that multi-factor model that I showed you earlier, and specifically it's a two-factor model with two latent factors here. And we can see the longer double-sided arrow here, two-pointed arrow here, of point, and see that the covariance, or more specifically here, because it's standardized, we can interpret this as a correlation, is 0.24. So when standardized, again, a covariance can be interpreted as a correlation. In a CFA model, covariances between latent factors help us understand the extent to which those latent factors are related or unrelated to each other. And we can also have covariances too with other observed variables too that might be in our model as well. Now, let's shift gears a bit now and talk about average variance extracted, or AVE, as well as composite reliability. Now, although not a parameter estimate per se, average variance extracted, or AVE, is a useful statistic for understanding the extent to which indicator variations can be attributed to the latent factor. So AVE takes into account the factor loadings and the residual error variance terms associated with a latent factor when it's computed. So in general, we consider AVE values that are greater than or equal to 0.50 to be acceptable. Now let's talk about composite reliability, or CR. So like average variance extracted, or AVE, composite reliability is not a parameter estimate. Instead, it is another useful statistic that helps us understand our CFA model. So composite reliability is also known as coefficient omega, and it provides an estimate of internal consistency reliability. You might be familiar with Cronbach's alpha, which is another indicator of internal consistency reliability, or in other words, another way that we can estimate internal consistency reliability for a multi-item measure, for example. So in general, we consider composite reliability values that are greater than or equal to 0.7 to be acceptable. However, we might relax that cutoff to 0.6 and label the reliability as questionable if it falls in that 0.6 to less than 0.70 range. So let's finish up by talking about model comparisons and how we compare two or more confirmatory factor analysis models. So when we're evaluating CFA models, especially multi-factor models, we often wish to evaluate whether a focal model performs better or perhaps worse than an alternative model. So comparing models can help us arrive at a more parsimonious model, or a simpler model that still fits the data well. It also helps us evaluate the dimensionality, meaning are there multiple dimensions at play here that we need to represent with separate latent factors. So as an example, let's imagine our focal model has two latent factors and unique sets of indicators that load onto their respective latent factors. Now imagine we also specify an alternative model that has just one latent factor, and all of those indicators from our first model, they are going to load onto that single latent factor in our alternative model. Now, we can then go about and compare these two models to determine whether the alternative model fits the data about the same as our focal model or worse. And if the alternative model fits about the same, it's going to be, in this case, our more parsimonious or our simpler model. We'll probably want to go with that model instead, because we usually want to be in favor of parsimony or simplicity. Go with the simplest, best fitting model possible. So if we're doing a nested model comparison, there's a certain set of procedures that we can use. Now, if you need help remembering what a nested model is, well, a nested model has all the same parameter estimates of a full model, but has additional parameter constraints in place. Meaning that, for example, we're constraining a factor loading, or we're constraining a covariance term between two latent factors, for example. But other than that, the models are the same. Now, if two models are nested, we can compare them using the model fit indices like CFI, TLI, RMSEA, and SRMR like we already went over, and so hopefully you're comfortable interpreting those indices. And so generally, whichever model has better levels of those 4 different fit indices, that's going to be the better fitting model. But we can also use what's called the chi-square difference test or a likelihood ratio test to compare the nested models too. And this is actually going to give us a statistical test of that nested model comparison there, meaning that we're going to have an associated p-value that we can evaluate statistical significance with. So what do you do if you have non-nested models, and how do you compare them? Well, for non-nested model comparisons, we can use other model fit indices like the Ikake information criterion, which is abbreviated as AIC, or the Bayesian information criterion, which is abbreviated as BIC. So for both of these, both the AIC and the BIC, the best fitting model will have lower AIC and BIC values. So the lower the better when it comes to AIC and BIC. Now, there aren't any absolute cutoffs or rules of thumb when it comes to interpreting those directly. It's really about comparing those values between 2 or more models. So this wraps up the video on confirmatory factor analysis. In the video, we did an overview of confirmatory factor analysis. What is it? It's part of the structural equation modeling family of analyses, and it helps us evaluate and estimate model structure, and specifically the measurement model. And often when we're doing it for psychological measures, it's going to help us evaluate the measurement structure for a multi-item measure of some sort, like role clarity, task mastery, or extroversion, which were the examples in this video. We also learned about path diagrams and how we can use them to visualize our models, and specifically our CFA models, which can help us understand what parameters that we've constrained or specified in our model or are allowing to freely estimate. We also learned about different types of model identification, so whether a model is just identified, over-identified, or under-identified. We also learned about model fit indices and cutoffs for those model fit indices. And then we finished up learning about the different parameter estimates in our CFI models and how we interpret them, as well as how we would do model comparisons, whether that's a nested model comparison between 2 competing models or a non-nested model comparison. So if you need some additional resources when it comes to latent variable modeling and structural equation modeling in general, which again, CFA is one application of structural equation modeling, I recommend checking out these 2 resources here that I have noted on this slide. And here are the references that I cited throughout the video here today. So again, this was a video on confirmatory factor analysis, and this wraps up that video.